Well, I tell you, I would feel remiss if I did not stand up here and talk to you directly, or as directly as I can in this virtual environment, about the central limit theorem. This theorem is screaming out to you to pay attention. It is called the central limit theorem because it is central to everything else we're going to do in the remainder of the course. Now, I'll tell you this. It is possible to get through the remainder of the course, and many of you will, without appreciating the role that the central limit is playing, or without maybe even understanding the central limit theorem. But if you really do want to understand what's going on, you're going to find that the central limit theorem is there propping up everything we're doing. Every opportunity that I get going forward, I'm going to point that out to you. So here it is. It's a mouthful, to be sure. What it says is this. It says that as the sample size increases from independent samples that you're taking, the samples that you're taking from some population with replacement, as that sample size increases, then a secondary distribution that you create from the means from each of those samples that you're taking, that secondary distribution will become normal. It will have a mean equal to the mean of this population, and it'll have a standard deviation smaller than this population by the square, by a factor of the square root of n. Now, holy Toledo! I mean, what the heck does that mean? How can you even understand it? I can only understand it if I sort of do a graphic. And as I've been thinking about what to say to you here, I'm pretty sure I've done this graphic elsewhere in this course, so you're probably going to run across this again, but so be it. You need to see it probably a couple times to get this. So what it's saying is, let's take an original population, and I'm going to purposely draw the distribution associated with that thing as clearly not normal, okay? There's a not normal distribution. So what this thing is saying is, if I start to take samples, here's a sample right here. I'm going to call it S. I just call it S sub I. I'm going to call it S sub 1. And it is going to be the set of all points x1, 1, x 1, 2, x1, 3, dot, 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 x1, n. There's my first sample. And if I took a mean of that sample, I would get x bar 1. Sample 1 has x bar 1. Let me take a second sample, again, of size n. So what's that sample look like? Well, that's x2, 1, x2, 2, x2, 3, dot, 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 x2, n. If I add those guys all up and divide by n, I get another mean, a sample mean. So these things are called sample means. These are the samples. Now let me just keep doing it, man. I'm going nuts with this. Down here someplace is S sub m. It's x1 m, x2 m, dot, 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 x m, n. Again, 1, 2, 3, dot, dot, dot. There's n different elements in that sample, and it has also a sample mean of x sub n. Now, if I take enough of those, I can then sort of create my own distribution of these numbers, these sample means. And that distribution is going to have a mean. It's generally called mu of x bar, and it's going to have a standard deviation of sigma of x bar. This original distribution has a mean of mu and a standard deviation of sigma, right? What the central limit theorem says is, as n gets larger and larger, mu sub x bar gets closer and closer to mu, and sigma sub x bar gets closer and closer to sigma all over the square root of n. These things are highly related. Now, there's some requirements here. The requirements that each one of these samples be independent independent. Yeah. The other requirement are that they be not too big, right? Less than 10% the total sample size. That's usually not an issue. But here's this last one is the huge one. It says that either, for this to be true, either this needs to be a normal distribution itself, or big, or n just needs to be bigger than 30. So in the case that n is bigger than 30, these sample sizes are bigger than 30, you don't need to know much about this thing. You certainly don't need to know its shape. You need to know its mean, you need to know its standard deviation. And from that, you can write down this sampling distribution. Now, two things before I pause and erase the board and come back and do an example for you. What the heck are those two things? These two things are, we're talking right now about the central limit theorem applied to sample means. But in fact, you're going to see in the open text that it also, there's a second central limit theorem applied to sample sums. You're going to find that there's a third central limit theorem that applies to sample proportions, right? It's a little bit more complex than we're showing in this elementary statistics class. And then the last thing I wanted to say was, oh, by the way, sometimes the central limit theorem is stated in a much more definitive manner. It says that if you take all of the samples of size n, take all of them, then mu sub x will be equal to mu, sigma sub x bar will be equal to sigma divided by square root of n. Right? I kind of prefer this kind of operational, the bigger n gets, the closer these approach. But one way or the other, you can see that as you use this, you're going to end up equating these and moving on. So let me stop right here for a second, erase the board, come back, we'll do a problem. Now, with the central limit theorem, what we're doing for the remainder of this chapter is a number of application problems. And I've got to tell you, those problems have to look an awful lot like the problems that you're doing in the previous chapter. There's an important, though initially it might look like a somewhat subtle difference to you. So here's a problem that we'll do. This says AC Nielsen Company. AC Nielsen is a company that polls and surveys people who watch television. They say children 2 to 5 watch on average 25 hours per week. And if you let the number of hours that any child watches per week be a random variable, then that random variable is normally distributed and it's got a standard deviation of 3 hours. The question is this: if you grab 20 such children between 2 and 5, find the probability that they watch 26.3 or more hours per week. So, maybe some of you are out there right now and pulling out the calculator, going to second distribution. Come on, second distribution, run it down to normal CDF, and maybe you're ready to throw 26.3, plus 99999 or 1E99, e to the 25, sigma equals to 3, and that's just as you did in the previous chapter. We kind of write that down. So again, what we're doing is we're looking at a distribution here, these children. We're asking, what's the area, the probability of this value x being greater than 26.3? Okay, what's the difference here between this problem and the problem you've done before? Because you would have just before gone lower, 26.3, upper, I'm going to go 1E99. Seems like the cool kids are doing that. Mu is equal to 25, sigma is equal to 3, paste and let's go. Why wouldn't you do that? The reason you wouldn't, it was because that is the answer to the question, what's the probability that for a given child, that given child watches 26.3 or more hours per week. And that's not what was asked. What was asked was grab 20. What's the probability in that case? Well, if you were to grab samples of 20, you could create, through the central limit theorem, a second distribution. That's normal. I don't know what this one is, but this distribution has the same mean as this. U sub x bar equals 25, and it has a standard deviation related to this standard deviation, the original population, equal to 3 divided by the square root of 20. Okay, so this is the distribution for samples of 20 children, and that's what was asked for. So we can do exactly what we're doing here, but let's make sure that we're working with the sampling distribution, the distribution of the sample means. Got to put square root of 20 in there. So I've kind of loaded up the calculator to do that. I'm going to hit paste. I'm going to hit go. And the calculator is going to come back and say this area right here, this probability is 2.63%. Very cute that the answer is the same thing as that number. Try not to let that confuse you, okay? So that's the difference, the fact that you're looking at groups, in this case of 20. All of these problems in this chapter will be the same thing. They will ask you for probabilities associated with groups of samples of certain sizes. You can't miss that. If you do, you're going to end up doing the wrong problem. You've got to make use of the central limit theorem, recognizing that the distribution that you're interested in is the sampling distribution and has a different standard deviation. Okay, good enough.